In this video, I'm going to explain you about the necessary and the sufficient condition for equimomental system. So this is very important for your exam point of view. So please study this. So the statement of the necessary and the sufficient condition for equimomental system is given by statement is the two systems are said to be equimomental system if and only if the two systems should have the same total mass, they should have the same centroid, and they should have the same principal axis and the principal moment of inertia at the centroid. Okay, so if these three conditions are satisfied, then we say that the system is equimomental, or if the system is equimomental, then these three conditions should be satisfied. So we are going to prove this theorem. So according to this theorem, let us assume first the three conditions are satisfied, and we'll try to prove that the system is equimomental. Okay, we assume the three conditions are satisfied. So if the condition 1, here we have taken already, we are taking the condition 1, 2 and 3 holds, means these three conditions are satisfied. They have the same total mass, they have the same centroid, they have the same principal axis and the principal moment of inertia at the centroid. So I'm taking two bodies, so I'm taking one diagram here. So this is one body and this is another system. This is first system and this is the second system. So there are two bodies, they have the same centroid, both of them they have the same centroid. Okay, so I'm taking one line along passing through the centroid that is taken as lambda. So the moment of inertia about this line is taken as I lambda. It's the moment of inertia about this. We'll try to find what will be the moment of inertia about this system, this line. Okay, so we are going to find about this line, and the direction cosine of this line is taken to be lambda, mu and gamma. So m is the total mass for each system, so the mass of this one is capital M, and here also the mass of this is capital M. So here we are taking let M be the total mass of the system and G be the common centroid of both the system. Okay, and we are taking here A star, B star and C star be the principal moment of inertia, as well as since they are the principal moment of inertia, the product of inertia will be 0. So at the principal moment of inertia about the principal axis, so that's why the product of inertia is 0 through G for both the system, and lambda be any line in space. We are trying to take a line in space, and I'll try to find the moment of inertia of this system about this line and this system about this line. If we get that the moment of inertia is same, then they are equimomental. Okay, they are equimomental. So we are taking that, so a moment of inertia about any, so we are taking let lambda be any line in space with direction cosines lambda, mu and gamma. We draw a line lambda dash, means same according to this, we draw a line lambda dash parallel to lambda with the, since lambda passing through the centroid, okay, passing through G, and the distance from this line to this line, I'm taking perpendicular distance from these two lines is nothing but it is h from lambda. Okay, then moment of inertia about this line. Okay, we have this G above this line. Since these two lines are parallel, they'll have the same direction cosines. Okay, since these two lines are parallel, will have the same direction cosines. So lambda, mu and gamma. So we know that moment of inertia about any line lambda dash with given direction cosine is what we have done already in the previous video as well as documents I have explained you. So the moment of inertia is given by I lambda dash A star lambda square plus B star mu square plus C star gamma square minus 2D lambda x, that D, E and F are also there, but since these are the principal moment of inertia, this D, E, D star, E star, F star will be 0. So we get the moment of inertia about the line lambda dash is nothing but it is A star lambda square plus B star mu square plus C star gamma square by the para-axis theorem. Okay, now we use the para-axis theorem. Since these two lines, if we look these two lines, this line and this line, they are parallel to each other, so I can use the para-axis theorem to find the moment of inertia about this line. So the moment of inertia about this line is nothing but is equal to the moment of inertia about this line plus the mass of the whole system into the distance, perpendicular distance between these two lines. So we have here by para-axis theorem the moment of inertia. But the moment of inertia of both the system about lambda is given by I lambda equal to I lambda dash plus mh square. So I lambda dash, you know, this is this a star lambda square plus b star mu square plus c star v square plus ms square. So this is for the first system. Okay, for both the system, if you take the first system also, this will be the moment of inertia, and if you take the second system also, the moment of inertia about the line lambda dash will be this. Now we can see that they have the same moment of inertia about a line in space, about the line lambda in space. So by the definition of equimomental system, if two bodies they have the same moment of inertia about any line in space, then they are said to be equimomental. So that's why the two systems are nothing but they are equimomental. Here, so you can see here, so we have here, hence both the systems have the same moment of inertia about any line in space. So hence the two systems are equimomental. So others I'll explain in the next video. Thank you.